oil. So, next we will consider the expression of mass transfer coefficient, how it takes care in case of how it looks like in case of gel layer control filtration. That is very important parameter, design parameter, and we will come to it once again. So, mass transfer coefficient is very important design parameter as far as the membrane operations and design of the membrane systems are concerned. So, let us first write the expression or definition. From definition, we start the expression of mass transfer coefficient K times Cg minus C naught. If you remember, it was Cm minus C naught in the earlier case. Now, in this case, it will be Cg minus C naught minus d del C del y at y is equal to 0. So, you can make it non-dimensional. So, you divide both sides by C naught. So, this becomes K times Cg star minus 1 is equal to minus d by h del C star del y star, and this becomes y star is equal to 0, right. So, you will be having Kh by d is nothing but minus del C star del y star at y star is equal to 0 divided by Cg star minus 1, and you can replace h by d by 4 and define the Sherwood number. What is the Sherwood number? Nothing but K times d equivalent by diffusivity. So, you will be getting 1 by 4 Sherwood is equal to minus del C star del y star at y star equal to 0 divided by Cg star minus 1. Okay. So, now what we can do, we have already the expression of del C star del y star in terms of y star delta etc., and evaluate that profile at y star equal to 0 and substitute that here. So, if you do that, what you will be getting is that Sherwood divided by 4 is equal to 1 over Cg star minus 1 2 times Cg star minus 1 divided by delta star. Okay. This will be cancelled out, and we know the expression of, so what is Sherwood number? Sherwood number just becomes 8 by delta star. And we know we have already got an expression of delta star or the thickness of boundary layer as a function of x star, and we are going to substitute it there. So, if you do that, you will be getting a profile of Sherwood number as a function of x star, and this becomes 8 by 192 raised to the power 1 upon 3 Reynolds Smith d by L raised to the power 1 upon 3 Cg star to the power 1 upon 3 x star to the power minus 1 upon 3. Okay. Now, you can do a length averaging. You can integrate this equation out over the whole length from 0 to 1, and it is basically integration of this quantity from 0 to 1, and this returns a value of 1.5. Okay. So, you will be getting 2.08 times Reynolds Smith d by L raised to the power 1 upon 3 times Cg star to the power 1 upon 3. So, that is the expression of Sherwood number or mass transfer coefficient in case of gel layer control filtration, where the under the 2-dimensional analysis when the mass transfer boundary layer is still developing. Okay. So, that gives the more or less an overview of how to obtain the permeate flux or Sherwood number or mass transfer coefficient in case of steady state system. But the most realistic case in case of gel layer control filtration will be that gel layer will be depositing over the membrane surface at constant concentration Cg star or Cg star is nothing but Cg by C naught at Cg, then its thickness is growing with time, and the growth, because more particles will be arriving on the membrane surface, it will be increasing its thickness. So, that will be offering more resistance against the solvent flux, and it will be decreasing, and because of the presence of turbulence outside the channel, the thickness or the growth of this thickness of boundary layer or the gel layer will be arrested, and you will be getting a steady state. So, more and in case of osmotic pressure control filtration, we could have done this analysis of the full transient. We did not do that. Why we did not do that? because it has been computed that the transient in an osmotic pressure analysis, osmotic pressure filtration system exists only for few seconds, let us say 10 seconds, maximum 1 minute. But in an actual operation will be of the duration of 4 hours, 6 hours, 8 hours. So, whatever is happening in within first few minutes or seconds, it is immaterial, right. You are looking for the final filtration characteristics. So, therefore, we did not do the transient analysis in case of osmotic pressure controlled filtration. On the other hand, transient analysis we did for the batch cell only, but for the start cell or the cross flow cell we did not do that. On the other hand, in case of gel layer control filtration in a rectangular cell or a start cell, the scenario is just different. Here the gel layer controlling filtration will be having much more prominent transients. This transient may exist for 10 minutes, it can exist for several hours, depending on the characteristics of the gel forming particle, porosity of the gel layer or cake layer, and how they are behaving. Okay. So, therefore, more realistic case of gel layer control filtration will be the transient analysis that we are going to do now. Okay. In this case, we will be considering gel layer as nothing but a cake layer, and the scenario will be something like this. This is a membrane, and this is a membrane, and this is nothing but the gel layer that is growing over the membrane surface, and beyond the gel layer there is the concentration boundary layer. And how this concentration boundary layer is formed? Because C is equal to C naught here, C is equal to C gel here. So, therefore, there is, and this C gel is basically at least 5 to 6 times, or sometimes in some cases it is 50 times of the bulk concentration. And because of this stiff concentration gradient, there will be existence of a concentration boundary layer, and over this the gel layer concentration is same. The concentration in this gel layer is always same at Cg. So, therefore, we can start our coordinate system from the middle. Let us say at when it is bulk, it is y equal to 0, and it is y is equal to delta here. Delta is the thickness of concentration boundary layer, and here it is at the membrane surface, it is y is equal to delta plus L. L is the thickness of gel layer. So, delta is thickness of concentration boundary layer or mass transfer boundary layer, and L is thickness of gel layer produced by the gel forming particle. So, therefore, now you see, having a particular turbulence in your system, that means if the Reynolds number is fixed or the startup speed is fixed, your delta will be a sole function of Reynolds number. So, this thickness will be fixed. On the other hand, the gel layer thickness will be growing in time in most of the cases. So, it will be delta will be, so L will be a function of time. So, in this case you are talking about a moving boundary condition, right. It is a moving boundary problem. This boundary is always moving, always increasing with respect to time of operation. Okay. So, this is the system, and you will be having a permeate flux, okay, out from the membrane. So, therefore, what we can do? We can do mass balance. We can write down the solute balance equation in various domains of this system. So, we write down the for y lying between 0 to delta, that means within the concentration boundary layer, the solute balance equation will be rho g dl dt is nothing but jc minus d dc dy. What is this? This is nothing but the accumulation term. Accumulation is equal to in minus out. Total accumulation of solutes, this is in and this is out, okay, because Cg is more than C naught. So, there will be backward frequent diffusion. And what is rho g? Rho g is nothing but the gel layer density. Or density of the particles forming the gel, and boundary condition at y is equal to 0, your C is equal to C naught and y is equal to delta C is equal to Cg. Okay. Now, so within this boundary you have to integrate this equation out to remove the y. Now, what is this equation? This equation is nothing but non-homogeneous ordinary differential equation. Okay, how to solve non-homogeneous ordinary differential equation? There are several techniques. You can break this equation into two parts: the homogeneous solution and the particular integral, and then you can get the solution and add the two up. Okay, so you can you must have studied all these mathematical techniques in the first year. Okay, use that and carry out this and carry the integration over y over these two boundaries from 0 to delta, and whatever you will be getting is that you will be getting rho g times dl dt is nothing but j times Cg minus C naught exponential j by k divided by 1 minus exponential j by k. Okay. And k is nothing but d by delta, is the mass transfer coefficient. Okay. So, this gives the governing equation for L, the thickness, how thickness grows with time with the initial condition, that is at t is equal to 0, L was equal to 0. So, obviously, when at the start of the operation the gel layer thickness was equal to 0. Now, the story is not finished here, because j is also a function of time. We have to establish how j is varying with time. So, for that what we will assume that, if you remember the schematic I have drawn in the beginning of this class, that there is a concentration boundary layer, there is a gel layer and there is a membrane. So, gel layer resistance and membrane resistance, they are put in series. So, we can write the phenomenological equation to connect that. Phenomenological equation, and what is the phenomenological equation? That is, flux is proportional to the driving force, or flux is equal to driving force divided by resistance, and there are two resistances here, mu Rm plus Rg. Okay, where delta P is the operating pressure gradient, Rm is membrane hydraulic resistance, call it membrane resistance, Rg is gel layer resistance. Now, one can ask why we did not consider the membrane resistance in the steady state analysis, and we have answered, already discussed that issue, that when it becomes initially, because gel layer does not form from the very beginning. So, initially you have only membrane resistance becomes dominant, after some time gel layer becomes almost equivalent to its magnitude, then it predominates, and when the steady state is reached, gel is basically the most prevailing resistance and it will be dominating one. Okay. Now, this gel layer resistance, we consider this gel layer is nothing but a cake sort of layer, it is a cake layer. Okay. So, gel layer resistance can be written as Rg is equal to alpha 1 minus epsilon g rho g times L. What is alpha. Alpha is known as the specific gel layer resistance. Now, where from you get this equation? This equation obtained by a solute balance, and if you look into the filtration theory, in fact you should study that thing earlier in some earlier course. Okay, look into the filtration theory. There the definition of specific gel layer resistance, porosity, gel density, etc. all given. Okay, and it has a unit of meter per kg, and epsilon g is nothing but porosity of gel layer. Rho g is the gel layer density that we have already mentioned, and L is the thickness of gel layer. Now, alpha, the specific gel layer resistance, is a function of gel porosity and particle of the gel forming material, and it can be the simplest way one can have an estimate of alpha in terms of particle diameter and porosity, that is known as the Kozny-Karman equation. If you ever do the filtration theory, you will come to know all these characteristic equations. So, alpha can be written from Kozny-Karman equation, that alpha is nothing but 180 times 1 minus epsilon g divided by epsilon g cube rho g dp square. Again, it's an empirical relationship. Alpha can be, that means a specific gel layer resistance or cake layer resistance can be expressed in terms of gel porosity, diameter of the gel forming particle, density of the gel forming material by this expression. So, if you know epsilon g, if you know particle diameter, then you can calculate the value of alpha. Now, typically this alpha is a function of delta p, and depending on the characteristic, one can have whether the cake layer or gel layer is compressible or whether it is incompressible. Okay. Now, let us see what we get. So, we have the expression of so our aim is to find j as a function of time, and this will be delta p divided by mu rm plus rg, and what is our rg? Rg is nothing but alpha 1 minus epsilon g rho g times L. This alpha can be calculated from the fundamental equation of Kozny-Karman equation by epsilon g and dp. That means from the fundamental property of gel porosity and particle diameter, one can calculate the value of alpha. Okay, and then one can go to the expression of gel forming gel layer thickness, that is j by rho g times Cg minus C naught exponential j by k divided by 1 minus exponential j by k. Okay, with the initial condition at t equal to 0, L is equal to 0. Now, we have the, so you have the expression of j there. So, you substitute, so in this expression j is nothing but a function of L. Okay. So, you can substitute there, and you can substitute j as a function of L, j as a function of L. So, the right hand side of this equation is nothing but dl dt is some function of L. So, this is an ordinary differential equation, and with an initial value problem. So, it is an IVP problem, IVP ODE. So, it is an initial value problem, ordinary differential equation, and this can be solved by trial and by Newton by RK4 method. Okay, maybe Runge-Kutta 4 method can be used to numerically integrate this equation, or you can use Euler's equation, you can use Adam-Bashforth equation, you can use various equation algorithms to solve this equation, ordinary differential equation. So, in the process, what you get? In the process, you will be getting L as a function of time. L as a function of time. Once you get L as a function of time, you can get J as a function of time. Okay? And typically, if you plot, the two plots are just opposite, J as a function of time, it will be something like this, and L as a function of time, it will be something like this. This is J, and this is L. Okay, this is gel layer thickness, and of course you will be reaching a steady state. Okay, and this steady state will be depending on mass transfer. So this is a mass transfer dominated region. This is the in between. It will be gel dominated region, and here initially it will be a membrane dominated region. Okay. So there are three resistances. One is the mass transfer, another is the gel, another is the membrane. So initially you will be having the membrane dominated region, then you will be having the gel dominated region, and when the steady state will be reached, you will be getting the mass transfer dominated region. And if you look into the expression of dl dt, I am just writing it once again. dl dt will be j by rho g Cg minus C naught exponential j by k divided by 1 minus exponential j by k. So if you talk about the steady state, this is a transient operation. If you talk about the steady state operation, now at steady state, your dl dt will be equal to 0, right. So what you get back? You get back the film theory equation, that is j is equal to k ln Cg by C naught, right. So at the steady state you will be getting the steady state equation that you obtained from the earlier analysis we have just done in the earlier class, that is j is equal to k ln Cg by C naught. Now what is the expression of k you will be putting? It will be either you will be putting the Levex equation, that is 1.85 Reynolds-Smith d by L raised to the 1 upon 3, or 2.08 Reynolds-Smith d by L raised to the 1 upon 3. In fact, the second formulation will be more correct. So the steady at the end of the transient, so in the gel layer control filtration, initially you will be having the transient, and this initial means it is not few seconds, it may be few hours. So it is very important here. At the end, whenever you will be getting the steady state, you will get the steady state flux from whatever we have done earlier analysis. Now if you look into the various parameters, now it is very difficult to get the exact parameters like alpha, that is the gel layer specific gel layer resistance, epsilon g, that is the porosity of the gel layer, and particle size, particle diameter. Now there is a point in this particle diameter dp, simply because we are using the Cosny-Kármán equation from the filtration theory to quantify alpha, or the specific gel layer resistance or cake layer resistance, but this particle diameter dp in the Cosny-Kármán equation is valid if you have hard spheres, right. If you had spheres, spherical particles, then you will be having the and of particles particular size, maybe 1 micron or 0.1 micron or whatever it is. But in most of the cases of membrane filtration, when we are talking about the gel layer controlling filtration, for example polyvinyl PVP, polyvinyl pyrrolidine, PVA, polyvinyl alcohol, or pectin, they are not spherical particles. For example, what is pectin? Pectin is nothing but a polysaccharide. It is a big chain, polysaccharide chain. Proteins, maybe some of the proteins like bovine serum albumin, it will be having ellipsoidal shape. You can consider it as a equivalent sphere. But what about these polymers like polyvinyl alcohol? They will not be of spherical shape. Like pectin, it will be a polysaccharide. It is not a spherical shape. So in these cases, you will be considering that whenever we are quantifying alpha is equal to 180 1 minus epsilon g divided by epsilon g cube rho g dp square, that means we are assuming that the gel layer resistance is equivalent to the resistance of equivalent spherical particles. Okay. So dp is nothing but the equivalent spherical diameter of these particles. Okay. So in most of the cases in membrane filtration, when we are talking about gel, the particles are not spherical in nature. So therefore we consider the equivalent spherical diameter of this particle. Now this is basically a point of contention of the issue, how to determine these parameters. It is very, very important to determine these parameters, but how to do that. So for that there are like if you remember the example of real retention, membrane permeability, what we did, these parameters, membrane performance parameter, we conducted separate set of experiments to estimate them. Like LP, the membrane permeability, we conducted experiments with distilled water and determined the value of LP. Similarly, we conducted the different separate set of experiments under high turbulence to estimate the value of real retention. Similarly, we have to estimate a different set of experiments to estimate various parameters in the gel layer control filtration. Now, we will look into those experiments or theory involved in those experiments, where we can identify how to estimate these different parameters. Those will be appearing in the equation of the gel layer control filtration. The first parameter. Okay. Now, next we will look the estimation of parameters. Above model means the model that we have just discussed. First parameter is estimation of specific cake layer resistance alpha. Cake or gel. Okay. How to estimate the specific cake layer resistance alpha? If you remember that alpha is basically appearing when you are writing the expressing the RG or the gel layer resistance in terms of length. Okay. So, for that what we have to do? We have to conduct one unstirred batch experiment like earlier. That is very important. That is the importance of conduction of unstirred batch experiments. Okay. So, to estimate alpha, we will conduct unstirred batch experiment with this gel forming solute, and this is very simple. It is a cell. It's a cylindrical shell where you just feed the material, set the pressure by using nitrogen cylinder or something, and let the system go as it is and measure the permeate flux. You need not to control anything anywhere. So, it is the simplest experiment in any laboratory. Okay. So, conduct unstirred batch experiment to estimate the value of alpha. How to do that? That we are just mentioning. The permeate flux J is written as 1 by A dV dt. Okay. What is A? A is nothing but the membrane area. And what is V? V is the cumulative volume of filtrate, the water that you are getting the permeate. Or this filter is nothing but the permeate. Cumulative volume, that means you are, as time you just monitor the how much you are collecting with time. So, just monitor V versus T data, just measure it. That is very simple. Either you can put the collect the permeate on a beaker, on a graduated cylinder, and monitor the volume that is collected, or if you don't want to do that, just put it on a balance and see the the weight that is gaining, and it is almost water. So, you know the density of water, you can get how much volume you are collecting, cumulative volume you are collecting. Now, we will go back to the phenomenological equation, that is J is equal to delta P divided by mu Rm plus Rg, and for a unstirred batch cell we just write J as 1 by A dV dt is equal to delta P divided by mu Rm plus Rg. Okay. So, you can rearrange it as delta P, you can take Rm out. So, this becomes 1 plus Rg by Rm, and this is nothing but, if you remember, this is nothing but pure water flux. We have defined earlier pure water flux, that is delta P by mu Rm. So, you can write it as Jw0 divided by 1 plus Rg by Rm. Okay. Now, what you can do, once you write that, then you can do a solute mass balance in the gel layer. We do a solute mass balance in gel layer. What is that? That means at any point of time, what is the mass of the solute that is arrested, that is present in the gel layer? What is that? L times A is the volume of the gel layer multiplied by 1 minus epsilon g, because epsilon g is the porosity. That much volume fraction is occupied by water. So, rest of that means 1 minus epsilon g is the volume fraction occupied by the particle. So, L times A times 1 minus epsilon g will be the volume of the gel forming particle, right. It should be multiplied by the density of the gel layer of the gel forming particle rho g. Okay. That will be giving you the total mass of the solute that will be present in the gel layer. And where from you got? Because you are getting it from C naught times V. What is the V? V is the cumulative volume that you have collected at that particular volume. So, that much. So, volume V was coming with the concentration C naught. So, C naught V is the total amount of solute that is arrested in the gel layer, and from the definition of the geometry of the gel layer and the characteristic of the gel forming material, we can get the mass of it. So, they will be equal. So, now you can invoke the definition of gel layer resistance. Rg was is equal to what is that? Alpha into 1 minus epsilon g rho g times L. Okay. So, I can write Rg is nothing but alpha times C naught times V over A. So, this L can be substituted as Rg divided by alpha 1 minus epsilon g rho g. So, combining these two, we can get Rg or gel layer resistance as a function of gel layer specific gel layer resistance and cumulative volume. Now, I am going to put in the phenomenological equation that we have derived earlier. If you do that, you will be getting 1 by A dV dt is equal to JW0 divided by 1 plus Rg by Rm, right, 1 plus Rg by Rm. I am going to write Rg as this. So, you will be getting alpha C0 by ARm times V, right. Now, everything, all the dependent variable will be in terms of V. So, basically what I did, I just replaced L in terms of V. Okay. So, just take it on the other side and you will be getting 1 plus alpha C0 by ARm times V dV A JW0 times dt. Now, we can integrate it out. That means, at time t from 0 to t, at time t is equal to 0, there is no filtrate volume you are getting. At time t is equal to t, you are getting a volume V. So, from 0 to t and 0 to V, you can integrate this equation out and see what you get. What you get is, you will be getting V plus alpha C naught 2 A Rm V square is equal to A JW0 times T. Okay. So, that is the expression you will be getting after doing the after carrying out the integration. Okay. Now, you can rearrange this equation and this will be T by V is equal to 1 over A JW0 plus alpha C0 2 A square JW0 times Rm times V. Now, what this equation says? This equation says that if I plot T by V versus V, it will be giving me a straight line. The intercept will be given by this quantity, the slope is given by this quantity, right. So, you will be getting a straight line something like this. Okay. So, the intercept is given by A 1 over A JW0 and the slope is given by this. That means, you conduct a batch cell experiment, just fill up the cell with the solute and with the solution, and then pressurize it, leave the solution at that particular pressure, go on monitoring what is the cumulative volume collected as a function of time, then plot T by V versus V. You will be getting a straight line. From the slope you will be getting the value of alpha, because C naught is known to you. You know the membrane area, that is basically pi r square. You know the initial permeability, the pure water flux, that is delta P by mu Rm, and you know the Rm. So, only unknown in the slope is basically alpha. So, from the slope, this slope is nothing but alpha C naught divided by 2 a square JW0 Rm, and from this equation you can get the value of alpha. Now, you conduct the experiment for a different delta P, you will be getting the value of alpha corresponding to that delta P. Now, you can set the operating pressure to a third one and carry out this experiment and plot this. So, you will be getting alpha corresponding to that particular delta P. In fact, if you plot, you will be getting the variation of, you will be getting different slopes with the variation of delta P, something like this. Okay. So, therefore, by conducting the batch cell experiment under various pressure, one can get alpha as a function of pressure. That means, for various pressure you can get the value of alpha, then you plot the value of alpha versus delta P. Okay. It may be a plot something like this. So, that means alpha can be expressed as a function of alpha naught times delta P raised to the power n. If this n is equal to 0, then alpha is invariant with delta P. In that case, the cake layer or gel layer is incompressible. That means the pressure does not have any effect on it, it will not compress, does not have any effect on it. So, in that case, this is incompressible. If n equal to 0, the gel layer or cake layer is incompressible. For n, typically generally this n becomes slightly low, less than 1, typically n is less than 1, and that means it is a compressible cake. Okay. So, those are different. So one can, so estimation of alpha is very clear to how to estimate the alpha. So, basically what you are going to do, it is very simple. You are going to conduct the experiment in a batch cell and monitor how much volume, cumulative volume you are going to get as a function of time. That means you are just collect the permeate on a let us say balance, and just keep on monitoring what is the time and this is the volume, what is the time, this is the volume. So, V versus T data, and plot T by V versus V. You will be getting a straight line. From the slope you will be calculating the value of alpha or specific gel layer resistance. Next, we see how to estimate the value of epsilon g, porosity of the gel layer, and particle diameter. Okay. Now, we do a derivation here, small derivation. Let us consider dP is the particle diameter, is that nothing but the molecular diameter. Okay. So, volume of one molecule or one particle is what? And we consider it is a spherical particle. Okay, that is the easiest way to start with. Volume of one particle will be nothing but V naught is nothing but pi by 6 dP cube, 4/3 pi r cube or pi by 6 dP cube. Now, volume of 1 mole will be how much? It should be multiplied by the Avogadro number. Okay, Na pi by 6 dP cube, where Na is nothing but the Avogadro number. Number of moles in 1 meter cube solution, let us say unit volume is 1 meter cube. is nothing but 10 cube multiplied by the Cg divided by the molecular weight. Cg is the gel layer concentration in kg per meter cube. So, if you divide by molecular weight, you will be getting number of moles, and this factor 10 cube comes out because this 1 meter cube solution you have taken. Okay. So, we write these quantities. Cg is nothing but the gel layer concentration in kg per meter cube. That is important. That is why this factor 10 cube is coming. Mw is the molecular weight. Of solute. Okay. Then volume of gel in 1 meter cube solution is how much? Volume of gel in 1 meter cube solution is nothing but 10 cube Cg by Mw multiplied by Na pi by 6 dp cube. Okay. There is the volume of gel in 1 meter cube solution. Now, what is the porosity, definition of porosity? Porosity is nothing but the fraction of volume that is occupied by water. That means epsilon g is nothing but 1 minus this. This is the solid volume occupied. So, the liquid volume will be 1 minus that 10 cube Cg Mw Na pi by 6 dp cube. Okay. So, this is the relationship of the porosity of the bed and the particle diameter, equivalent particle diameter, if you are talking about a non-sphere or non-hard sphere particles. Okay. Now, we have the definition of alpha, that is alpha is specific cake layer resistance, that is related to the epsilon g and dp through Cauchy-Carbon equation, right. If you write down that alpha is nothing but 1 over 80 1 minus epsilon g divided by epsilon g cube rho g times dp square, and we have already seen this alpha can be a function of delta p if it is compressible. So, alpha can be written as alpha naught by delta p to the power n. We know how to determine the value of specific gel layer resistance by conducting batch cell experiments under different pressures. Once you do that, you can fit a curve something like this: alpha naught delta p to the power n is equal to 180 1 minus epsilon g cube rho g times dp square, and right just now we have derived a relationship of epsilon g as a function of dp. What is that? The epsilon g is equal to 1 minus 10 cube Cg molecular weight Na pi by 6 dp cube. This is one equation, this is another equation. So, for a particular delta p, the whole left hand side of this equation is known to you, and the right hand side it will be having a combination of epsilon g and dp, rho g will be known, and this equation gives you a relationship of epsilon g and dp if the value of gel concentration is known, and that will be known. So, you will be having two equations, two unknown. What is this unknown? Epsilon g and dp. So, these two equations can be solved by trial and error. You can use Newton-Raphson. Solve by trial and error, and you can estimate epsilon g and dp for various delta p. That means you can prepare a table of delta p for a particular delta p, what is the epsilon g and dp, for a particular delta p, what is epsilon g and dp. So, delta P1, delta P2, delta P3, epsilon g dP. So, various operating pressure, this bed porosity and particle diameter will be changed. Obviously, this method if you remember, this method is valid for the non-hard sphere solutes. That means, what I mean by that, suppose you are having a pectin gel and they are not hard sphere, right, they are polymeric. So, by changing the pressure, the gel will be compressed, the characteristic will be changed. By suppose the solute is fixed, that means the size will be fixed, but if it is a hard sphere, then we are not going to adopt this method. If they are hard sphere, we are not going to adopt this method, because in that case the particle diameter is fixed, the porosity will be fixed. So, everything will be fixed, but in most of the membrane filtration process, we are not talking about the hard sphere, we are talking about the polymers, we are talking about the polysaccharides, we are talking about the gel not forming of solids, but by the high viscous liquids. Okay. In that case, the equivalent particle diameter and equivalent porosity at that particular operating pressure can be estimated by this method. Okay. So, there is a subtle difference between the hard sphere and this non-hard sphere case. Okay. So, what we are meaning by that? That means, delta P1 your dP will be something, in delta P3 or under the delta P3 operating condition your dP will be something else. That means, this bed will be having an equivalent resistance of solutes having uniform particle diameter dP1 under the pressure delta P1. Same bed under the different operating pressure delta P3 will be having the equivalent diameter dP3 maybe. Okay. Because the particles are not hard sphere, they do not have actual dimension all the time, they will be compressible. Okay. So, that is the thing. Now, you have estimated all the parameters except one parameter, that is the how to estimate the gel layer concentration, that is very vital. For estimation of gel layer concentration, if you remember the permeate flux under the steady state, J is equal to K times ln Cg by C naught. Okay. This is the expression, film theory expression of permeate flux under the steady state operation. Now, what we can do, we do not know what is the value of C gel. Okay. What we will do, we will take different concentration, various concentration of the solute and carry out the filtration experiment and wait for the steady state is being reached. Okay. Now, we keep the same mass transfer coefficient, we maintain the same mass transfer coefficient. How to maintain that? If we maintain same hydrodynamics in the channel, the mass transfer coefficient will be same. That means, we are going to conduct number of experiments under the same starting speed or same cross flow velocity. That means, same hydrodynamics. So, we conduct let us say 10 experiments, 10 complete experiments by taking 10 concentrations, maybe 1 kg in one case C naught maybe 10 kg per meter cube, in another case C naught maybe 20 kg per meter cube, another case it may be 25 kg per meter cube, and maybe 40 kg per meter cube, like that. We consider we conduct experiments, separate independent experiments by considering various concentrations of the feed solute and under the same hydrodynamic conditions, and measure and in every experiment we wait for the steady state to be reached, maybe after half an hour, maybe after 1 hour. Okay. once the steady state is reached, then we measure the steady state permeate flux. Okay. Now, we plot the steady state permeate flux versus feed concentration in a semi-log plot. J steady state versus concentration. This will be normal, this will be logarithmic scale. And if you look into the expression, J is equal to K ln Cg minus K ln C naught. Okay. So, the plot of JSS versus ln C naught is supposed to be a straight line with a decreasing slope, because there is a minus sign present. So, you are going to get a curve something like this. Okay. So, these may be the experimental points of the steady state flux at 10 different feed concentration. Okay. You will be getting almost a straight line of decreasing slope. Now, you are going to extrapolate this thing. You are going to extrapolate this thing, and the point where J becomes 0, that particular concentration becomes gel layer concentration, C gel. All these 10 experiments have been conducted with the same mass transfer coefficient. You can conduct these 10 experiments with a different mass transfer coefficient or different starting speed or different cross-flow velocity. If you do that, then this will be K1, then you are going to get another straight line, maybe del triangle, 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 and all these experiments are conducted with a mass transfer coefficient K2. Then if you can extrapolate, they will converge almost at the same gel point. Similarly, you can conduct experiment for a different mass transfer coefficient, let us say K3, and they will be converging on the same gel point. So, that is how the gel layer concentration will be evaluated. So, if you plot this in a semi-logarithmic plot, the concentration that will be extrapolated will be the gel layer concentration. Concentration as Cg. Now, so basically you have to conduct number of experiments independently and evaluate and analyze those data, and will be independently estimate the gel layer concentration. So, in this gel layer model, the several parameters there, those will be appearing. So, you will be having tools or method to estimate them separately, independently, and then you can use those data and can find the can use the gel layer controlling filtration model under the steady state condition. Okay. So, I will stop here. So, we will continue this thing in the all these discussions in the next class. Thank you.